Hello, welcome to my talk on channel duality. Let me start by sharing my screen. Yeah, I'm Narayanan. I'm a postdoc at the University of Arizona with Professor Bane Vasic. So this work is joint work with one of my PhD supervisors, Henry Pfister at Duke. So we are going to talk about a notion of dual channels and focus on a special case. So we are very familiar with the notion of code duality. So if we define a binary linear code as a subspace of the binary n-bit vector space, the dual code is just the set of all vectors that are orthogonal to the code words in the code C. So this duality is just based on linear algebra, and this has been used ever since coding theory came into practice. So we have used this duality in many ways. So one particular form of duality was used in this paper by Hartman and Rudolph, where they showed that ML decoding for a high rate code can be done efficiently by converting the sum on the code into a sum over dual code. So this is a more refined version of the identity they used. So here you have some product, sum over a code, and you have a product over functions on the individual bits, and this transforms into the sum over the dual code, which is scaled, and now the functions are Fourier transforms of the initial functions. And in fact, the McWilliams identity on weighted enumerators can be derived using this identity. So basically, an indicator function over the code transforms into the indicator function of the dual code scaled by the parameters of the code. So this duality is very useful, and now we want to investigate if there is any kind of duality that is also true for channels. So let's start with the binary erasure channel. So it is well known that for the binary erasure channel with parameter epsilon, where epsilon is the probability with which the bit is erased, and 1 minus epsilon is the probability with which the bit is received intact. So the capacity of BSC of epsilon is known to be 1 minus epsilon, and similarly, just by switching parameters, the BSC of 1 minus epsilon has capacity epsilon. And you see that the sum of the capacities is exactly 1, which is log of the input dimension. So this, is a tight coupling between the capacities of the channels. And another way to express this would be to use entropies. So here's a more concrete way to see this. So if you transmit a code word of a code and through the primal channel, and say the set of erased indices is given by script E, and you want to ask the question, when can I recover the ith bit? And now you consider transmitting a dual code word over the dual channel, and now the erased indices are the complement of the set, so it's script E complement. And again, you want to ask the same question. And with some thought, you can prove for yourself that the ith bit cannot be recovered in the first case, if and only if it can be recovered in the second case. So this is just by investigating, what the erased indices do and assuming ML decoding. And more generally, the performance of a code on the BSC of epsilon is completely characterized by the performance of the dual code on the dual channel, which is BSC 1 minus epsilon. So this can be established in terms of entropies, in terms of exit functions, in terms of block error rate, and so on. Now, can we extend this beyond the BSC case? Can we define a more general version of dual channels? So this is what Joseph Renes did in 2018. So he considered the class of channels which have classical inputs but quantum outputs. So for example, any classical channel can be embedded into a CQ channel simply because classical outputs are special cases of quantum outputs. So this includes all classical channels. And he defined the dual channel in a particular way, which has some details. So in the interest of time, we'll not discuss that in the talk. But so he defines a concrete notion of dual channel. So he shows that this kind of an entropic duality is true. So the entropies, so these are actually conditional entropies. So this is the conditional entropy of the input given the output. And so if you consider the Shannon entropy, the dual entropy is itself. And so this H bar would just be H. And the sum of the entropies is exactly equal to the log of the input dimension, which is what was true for the BEC case. So for more information on dual entropies, you can see this nice monograph by Mankaramamika. So this is the very general version of duality he proves. And in this talk, we will arrive at this sort of a result using just linear algebra for a particular pair of primal and dual channels. So what we'll look at is channel coding on the channel W and secrecy on the dual channel W perp. Now let me clarify that when I say secrecy on the dual channel W perp, what I mean is that you have a secret message, but the channel to the intended recipient is perfect. But the channel to the eavesdropper is W perp. So, so only the channel to the eavesdropper is non-trivial. So in this case, if you consider these pair of dual entropies, H min and H max, then it's true that the 1 minus the block error rate, which is the block success rate, is related to the min entropy, and the secrecy metric for the problem on the dual channel is related to H max. So this metric basically establishes, how close is the posterior for the eavesdropper, close to the uniform distribution, which is the prior on the message. So you basically don't want them to get any information about the secret. So we will establish this equality for these two channels. So W is the pure state channel with parameter theta, which we will define shortly. And the dual channel is known to be the binary symmetric channel whose parameter is coupled to the primal channel in this form. So we'll establish this duality in this talk using both entropies and later just using linear algebra, using like factor graph duality and linearity of codes. So for coding on the pure state channel, the metric we'll consider is the block success rate, which is 1 minus block error rate. For secrecy, as we said before, the channel to the eavesdropper is W perp. And so we care about the distance between the posterior distribution that the eavesdropper has based on what information he or she taps, and the distance between the posterior and the uniform prior on the messages. This is quantified by the Bhattacharya distance squared. So the outline of this talk would be to start with the BSC duality, look at it using entropies, generalize it to these pair of channels, and finally use factor graph duality to prove this just using linear algebra. And thereby we'll ignore a lot of quantum information machinery. And hopefully this is more accessible and you get a different kind of intuition. Okay, with that said, let's jump into the setting. So for coding and secrecy, we have this sort of unified setup. So consider any binary vector X. Now we are going to split the vector into two vectors. One is a code word in your code, and the second part is going to be a complementary code word. So what I mean by that is you consider a binary invertible matrix A, where the top k rows define a generator matrix for your code, and the remaining n minus k rows define a complementary code. And what you're going to do is express this vector X as the sum of a code word, which is given by the message times the generator, plus a coset selector times this matrix F. So in channel coding, you would care about decoding this message U given the output of the channel. For secrecy, we are using Weiner's coset coding approach. So where the coset selector is the secret message. So you select the coset of your code and then randomly pick some vector in that coset and transmit over the channel, so that you are hoping to confuse the eavesdropper as much as possible. So now you can look at the same vector as being summed over the dual code word and a dual complementary code word. And so this is just another binary invertible matrix whose last n minus k rows is the parity check matrix for your code, or the generator matrix for the dual code. And E is the complementary code to the dual code. And so the primes indicate that we are using the dual codes. So this is the setting. And like we saw in the previous BEC slide, so for channel coding, so script E is the set of erased indices, whereas for the secrecy problem using the dual code on the dual channel, script E will be the unerased bits. So script E complement would be the erased bits. And here we can show this kind of duality. So the conditional entropy of the input for channel coding given the unerased outputs, plus the conditional entropy of the secret message for the dual code of the dual channel sums exactly to K. So for intuition, you can see that if this entropy was 0, meaning you can perfectly recover the message, then you also have perfect secrecy because this metric is maximum being k. And so this is the kind of intuition that can be generalized now beyond the BEC case. And we are going to look at the case of the pure state channel. So how is the pure state channel defined? So the input is classical, it's a bit. The output is a qubit, which is a two-dimensional vector. And it's modulated by the input using this sign. So when x is 0, there is no minus sign here. When x is 1, you have a minus sign. And theta is the channel parameter, which you can assume lies between 0 and pi over 2. Now, you can see a nice symmetry between the outputs. So you can switch between the two outputs, theta and minus theta, just by applying this poly Z matrix. So, and so because of the symmetry, if you transmit an n-bit vector over n uses of the channel, so it's a memoryless channel, the output can be written as this fixed state theta tensor n, modified according to applications of Z matrices wherever the vector is 1. Because when you apply a Z matrix on theta, you get minus theta, which is the output when x is equal to 1. So this is a nice symmetry. And so when you consider a code and a set of all code versions of code, if you look at all the possible channel outputs, these are your hypothesis states. Then these form this what's called the geometrically uniform symmetry, where you can start with a fixed state, and the action of this group of Z matrices gives all possible output code words. Okay. Given this symmetry, you construct this matrix capital Phi, whose columns are, the different possible channel outputs for the different code words. So you have 2 to the k columns, and each vector is of length 2 to the n. That's why you have 2 to the n rows. Now, what we care about is, at the output of the channel, before you do any measurement on the state, your prior is uniform on all the code words. So this density matrix is just a mathematical way to write this. So just an equal mixture of all code words. And what we'll care about information theoretically is the one Neumann entropy of this density matrix, which is known to be just the Shannon entropy of the eigenvalues. So all you need to know about the uncertainty in the output is diagonalize this density matrix and then compute the Shannon entropy. Okay, so this is the result we first established. So we know from linear algebra that both of these matrices, phi, phi dagger, or phi dagger, phi, have the same non-zero eigenvalues. And we show that they are diagonalized with a Fourier transform, and the eigenvalues are given by these functions s hat for different k-bit arguments h. So we'll see what s hat means shortly. The nice thing, though, is that we can also show that the same s hat function is the posterior distribution for the eavesdropper, whose channel is the BSC with the dual parameter. When you're doing secrecy using the dual cosets of the dual code. So this is overall what this means is that the output entropy for coding on the pure state channel is exactly the conditional entropy on the input for secrecy on the BSC. Using this, what we can do is we can write down the conditional entropy for channel coding on the pure state channel, and just using properties of entropy, we can split it into 3 terms. And by plugging in the right values, we can see that the conditional entropy for coding on the pure state channel plus the conditional entropy for secrecy on the dual channel, which is the BSC, equals k. And this is precisely a generalization, of the BEC setting. It's the same phenomenon. So this is the kind of intuition we want to convey here. Okay, in the final part of this talk, I will focus on, so we already saw the entropic view of duality. And in this last part of the talk, I'll show that the metrics for the 2 problems. So coding on the pure state channel, the metric is the block success probability. And for secrecy on the binary symmetric channel, the metric would be this Bhattacharya distance. So we'll show that these 2 are equal without using much quantum at all. Okay, So the key, one of the key ingredients in our proof is the square root measurement. So you might be familiar with this least squares solution. So this is exactly also called the least squares measurement. So phi, remember, is our matrix of whose columns are code words. So the columns of this matrix psi define rank 1 projectors, which defines the measurement. And it's known that because of this geometrically uniform symmetry of our hypothesis states, this is optimal for decoding binary linear codes on the pure state channel. So this is easy to show. Now, what we care about is computing this block error rate, which involves computing inner products between our channel outputs and the measurement vectors. So Eldar and Forney in 2001 established that this inner product between the measurement vectors and the channel outputs is diagonalized by the Fourier transform, and the eigenvalues are given by this function sigma of h, which will be clarified in the next slide. And so if we want to compute these inner products and hence compute a closed form expression for the block error rate, then we need to compute these sigma of h values. Okay, so here, so to do this, the first thing we do is define what's called the overlap function. So for k-bit vector g, which is the argument of this function, the function is defined as the inner product between the channel output for the all zero code word, which is just theta tensor n, and the channel output for the code word corresponding to message g. So which we saw using the symmetry is the z function applied to theta tensor n. And this inner product can be easily seen to be cos theta raised to the Hamming weight of the code word. So this is called the overlap function. It's just the overlap between this code word and the all zero code word at the channel output. And then we define the Fourier transform. This is actually the S hat function, which we had defined earlier. And Eldar and Forney established that the sigma function in these eigenvalues is related to this S hat function. So now this is what we are interested in computing. The first trick we do to compute this, it's not easy to compute this directly. So we embed it in the n space. So this is now a sum over k-bit vectors. We actually make it a sum over n-bit vectors. But we only have to worry about, we only have to restrict it to code words. So we put the indicator function of the code inside. And we have the same function cos theta. The only non-trivial thing now is to sort of relate this -1 sign with this -1 sign, because this is over n-bit vectors, this is over k-bit vectors. And so we do this in more detail in the paper, but for the talk, we'll ignore those details. So we can relate this s hat prime function on the n-bit space with the s hat function. So which means our problem is now to compute this function. For this, this is where we established the relation to factor graph duality. So this is what we saw on the first slide. Sum over the code can be converted into the sum over the dual code. So this symmetry is, this identity is what we use to compute this in closed form, which means we effectively have computed sigma of h. Okay, so therefore, using that, we can give a closed form expression for s hat, which also gives a closed form expression for sigma. And using this, we can establish the inner products between the measurement vectors and the code states to be the Fourier transform of the sigma function. And finally, that gives the result that the block success probability, which is the 1 minus block error rate, is exactly the squared Bhattacharya coefficient between this s hat function and the uniform distribution. And we already showed that s hat is the posterior for the dual problem. And so this establishes the result. So to conclude, we reviewed PSC duality in this talk for coding and secrecy, and we generalized this to these pair of channels. And we proved that we gave an entropic version, and then we used just linear algebra and factor graph duality to show that these metrics are equal. In the longer paper, we discuss more details, and we also discuss the other version where we consider secrecy on the pure state channel and coding on the binary symmetric channel. So we invite you to look at our longer paper for more details. Thank you for listening. So these are some just backup slides which you can review. Thank you.